My name is Eugene Chang, and as chair of the Department of Astronomy, let me welcome you to the 2016 Raymond and Beverly Sackler Distinguished Lecture. The Sacklers give to our department so that we can host an annual public lecture to further the sciences and arts at Berkeley. The Sacklers aren't able to be here tonight, but they will be sent a video of this lecture. And so let me take the opportunity on behalf of everyone here to thank the Sacklers. Thank you so much from across time and space. Thank you. The Sacklers have given to astronomy, and as an astronomer myself, let me share an experience which I think may be common to many astronomers, which is that when I'm asked, what is it that I do, and I meet people off the street, I meet a person for the first time, they say, well, what is it that you do? I say, well, I'm an astronomer. And very often they react with great enthusiasm, very often, and they say, well, that's just so interesting. I always wanted to study astrology in school. And it's at that point that I have to explain to them that, when you go to the library, there's the nonfiction side of the library, and there's the fiction side, and astronomers, well, we want to write papers that's for the nonfiction side, although we don't always get it right, and so the things that we do sometimes have to be reshelved, but generally we're on the nonfiction side. I used to be irritated at having to make this distinction all the time, but in recent years, I've learned to actually see that there really isn't much difference between astrology and astronomy. And what does astrology posit? Astrology posits that the motions of the celestial bodies govern events on Earth. Broadly speaking, this is true. It's certainly true in detail for astronomers. I mean, my research life, which is basically my life, is dictated by what's going on up there. Take the following horoscope, for example. Pluto. Okay, Pluto, currently, true statement, currently in the constellation of Sagittarius. What does this mean? Well, according to astrologers, it augurs undue influence by Pluto on ideologies. Okay, according to Deborah McBride, an astrologer from Brooklyn, when Pluto is in the sign of Sagittarius, it signifies religious wars or cultural warfare. Now, cultural warfare, I think, accurately characterized the astronomical community back in 2006, when we, the astronomers, were bitterly divided over the question of whether to call Pluto a planet or not. On the one hand, you had the weight of history, the weight of thousands of school lunchboxes, the weight of astronomers whose grants in subtle ways depended on Pluto's status being preserved as the outermost planet. And on the other hand, you had the growing recognition, the new realization that Pluto was just one of a vast collection of icy, rocky bodies strewn in the space beyond Neptune that is collectively known as the Kuiper belt. Okay. At the center of that controversy was our speaker today, Mike Brown, whose discovery of a Kuiper belt object whose size was practically identical to that of Pluto really brought this debate to a head. And his discovery of a Kuiper belt object that he later named Eris, very aptly, Eris is the goddess of strife and discord. Okay, very appropriate. His discovery ultimately led the International Astronomical Union, the United Nations of Astronomers, the governing body for issues of nomenclature, to rule that in fact we've gotten it wrong all along, that there aren't, 9 planets in our solar system, that there are in fact only 8. There are only 8. It ends with Neptune. And Pluto and Eris are members of a new class of body, dwarf planets. Okay? And in recognition of Mike's, decisive role in demoting Pluto from its status, Time magazine named him one of the top 100 most influential people in the world. It's true, it's absolutely true. Los Angeles magazine recognized him as one of the most powerful Angelinos. And like all the great crime bosses of history, Mike wielded his power brazenly. He wrote very cheerfully, candidly, openly about his discoveries and all the politics surrounding the status of Pluto in a tell-it-all bestseller that he entitled How I Killed Pluto and Why It Had It Coming. Which I have to say, is one of the most vindictive titles I've ever heard. It should come as no surprise that Mike, as an astronomer whose discoveries have literally changed our culture, is a Berkeley alum. He was trained here in our department of astronomy. He received his PhD in astronomy working with Professors Hiron Spinrad and Imke de Potter, who Imke is here as a distinguished guest today. It is here at Berkeley that Mike was first introduced to the science of comets, which hail from the Kuiper belt. When you see a comet in the sky, yes, it came from outer space, but more precisely, many of them come from the Kuiper belt, from the outermost reaches of our planetary system, dislodged from those outermost portions, and corralled into the innermost system where we can see it as a comet. It's here at Berkeley where he first started pursuing his interest in these frozen, icy worlds. He's pursued and maintained that interest with spectacular success at Caltech, where he currently serves as the Rosenberg Professor of Planetary Astronomy. And it's this subject, Kuiper Belt science, that he's going to tell us about today as this year's Sackler lecturer. So please join me in welcoming Mike.
Thanks, Eugene. Thanks, and thanks for coming. Thanks for inviting me to be here. It's always fun to come back to where I did my PhD. I want to finish up some of the story that Eugene told, because he missed the important part of the story, which is, as you remember, Pluto in Sagittarius was auguring all these terrible things: cultural war, religious warfare, cultural strife. Yes. Terrible things. After it got demoted, all of that was fixed. So we don't. So this I think is even better proof that astrology is working just fine. So I'm going to talk a little bit about some of the things that Eugene talked about Pluto, about the discoveries in this region of the Kuiper belt that I'll show to you. And I'm going to show you how those have led us onto our new quest, which is to find the real ninth planet in the outer part of the solar system. We call it Planet 9 because we're not very creative. But when we actually find it, it'll get a real name. And I think I'm going to try to convince you today that it's really out there and that we really will find it. The story of another planet in the solar system beyond the one that we know of actually starts in something like 1790. In 1790, Uranus had just been discovered, and astronomers were interested in whether or not Uranus was a planet. Uranus was discovered by chance, but by chance of a very careful astronomer who was charting positions of things in the sky, saw something that looked a little bit unusual, it looked a little bit fuzzy, and he went back and looked the next day, realized it had moved, and that is and remains the key signature of something that's part of our solar system. It's moving compared to all the background stars. And this was William Herschel who made this discovery. And I sometimes try to step back to that moment in history, because this is, thinking about finding new planets is pretty exciting. But imagine this first planet ever discovered in history. All the planets up to that point, were all the way out to Saturn, could be seen with the naked eye. Everybody knew about these planets. Uranus was the first one that was discovered by a telescope. I've never been able to find anything written down about what a sort of psychic shock that was to humanity, to realize that the solar system was bigger than they possibly thought. There's a new planet out there. They didn't know for sure it was a planet at the time of discovery. They knew it was something in the solar system moving. And one of the things they thought it might be is a comet. They knew about these things called comets. They knew they were on these very elliptical orbits that went out quite far away, came back in. And so the question that everybody had at the time of the discovery of Uranus is, what kind of orbit does it have? Does it go in a circle around the sun, like all the planets do, an ellipse really, but we'll call it a circle? Or is it on a very elliptical orbit? The only way to figure out what kind of orbit it has is to sit and watch it year after year after year and see it as it goes around the sun. Uranus takes about 80 years to go around the sun. 80 years is a long time to wait. So in about 1820, an astronomer named Alexis Bouvard in Paris decided that he didn't want to wait 80 years to figure out the orbit. He was going to go back in time and see if he could find it. So what he did is he would go back a couple of years and look at other astronomers' data where they had drawn where all the stars were. And he realized, hey, this person drew a star there, but there's not a star there anymore. That could have been Uranus. And he says, okay, if that's it, I'm going to now go back another couple of years. There's a star where there's not supposed to be one. And he put it there and went back a couple of years. And he went back all the way to, if I'm going to show you this table just because you can't read it, he went all the way back to that very first thing on the top of that plot there is 1690 was the first time anyone had actually seen Uranus was 100 years before its discovery. And he has data now from 1690 all the way up to 1819. He went through this math that I'm going to now go through line by line. I don't even understand what all this is. Eugene probably does. Do you know what all this stuff is? He does. He's nodding yes. But the important thing here is that he has all the positions of Uranus from 1690 all the way up to 1819, and he proved in somewhere up here, he says in French, that it's on a circular orbit. He proves that it's really a planet. This is his big result. He also shows it's not quite where it's supposed to be all the time. The little pluses and minuses that you see here in the second column are how far away from where it's supposed to be that it really is, and it's kind of deviating here and there. And he does what any good theoretical astronomer does when presented with data that doesn't make sense. He decided that the people who were doing the observations probably were bad, and you shouldn't trust them. He actually says this here. It's difficult. I don't know. If you read in French, you can see it where he says it up here. He does mention the possibility, however, that there might be something else beyond Uranus perturbing its orbit. He then actually gave his observations, gave his data to an astronomer also at Paris, in Paris, Leverrier, and he said, you should try to figure this out. There might actually be something out there. Leverrier worked on it for a while and realized that he could explain these data very precisely with a planet beyond Uranus. Leverrier went to basically the French Academy of Science and presented his results, and they were all very excited, and they clapped in their very excited ways. Yay, nice job, Leverrier. And he was very excited, and he wanted them to go look for it because he could tell you exactly where it was, and it did not occur to them, I think, that you could use math to discover a planet. They didn't really think that this was reality. They really thought that this was a really beautiful mathematical demonstration that you could make the numbers work out, which is not the same as thinking that you can use physics and math to predict things. And he's like, no, there's really a planet. Go look, it's right there. And then, yeah. So nobody in France would look for this planet. He finally contacted the Berlin Observatory, and they opened up their telescope, pointed to exactly where he said it was, and they found it in the first night of his observations. There's Neptune was right there. And to me, these two moments, Uranus as the discovery of the first discovery of a planet, which just changes the way that people must have thought about the solar system. But Neptune, the first really good demonstration that math, this newfangled math and physics stuff, actually is describing reality. It's not just a cute trick to make calculations. You can actually find things you didn't know that were there based on this math and physics. And I think those two things were an incredibly powerful realization, and this is in 1845. There's an obvious thing to do. As soon as you have discovered a planet using math and physics, the obvious thing to do is to look for the next planet. So Uranus was discovered by accident, by careful observations. Neptune was discovered by math and physics. A slew of astronomers immediately started wondering, now it's obvious. There must be something else out there too that we haven't found. Let's go find it. So they started reanalyzing the orbit of Uranus, looking at the orbit of Neptune as observations were coming in, and trying to see if there was something else out there. The most famous of these predictions of another planet beyond Neptune, there was a series of people working on it, but the most famous one by far was from Percival Lowell. Percival Lowell predicted, he had a series of predictions, but the one that really hit home was the one that he called, I think he's the one who originally called it Planet X. This large planet beyond the orbit of Neptune that's perturbing the orbits of Uranus and Neptune. And he predicted exactly where he thought it was supposed to be using the same methods that Leverrier did to find Neptune. And he sent some astronomers up to Mount Wilson, which is in Southern California. Actually, it's literally my backyard. You can see the mount where he is. And they took a picture of the sky, and it looked something like this. And do you see the ninth planet there? No? Okay. He didn't see it either. The astronomers didn't see it. But they were looking for something big. They were looking for this sort of Jupiter-ish sized object that was tugging on Uranus and Neptune. And a Jupiter-sized object, it would be obvious. It would be like this big in the frame here, and you would take a picture and you just know. They didn't see anything here, so they went back. He went back to the drawing board, kept on doing calculations. He died before anything was ever found out in that region of space, but not before he founded the Lowell Observatory in Flagstaff and set them out on the quest for Planet X. In his quest for Planet X, in their quest for Planet X, they built a special telescope to look for it. They hired Clyde Tombaugh off of a farm in Illinois, and Clyde Tombaugh took a few pictures that looked kind of like this, and realized that he was smart enough to know that he didn't know what a planet looked like. And he was smart enough to remember all these things that we knew about planets, which is the real way you identify a planet is you don't look for that big disk in the sky, you look for something that moves. So he took a picture one night, and then he would take another picture the second night and watch it move. Did you guys see it move? Sure you did. Okay, let's try this again. Here's the first night. There's the second night. How many people think they see it? Okay, we'll see. Okay, we'll try. First night, second night. I don't know why, but if you repeat things 4 times, it's a function of physiology. The 4th time, everybody sees it. So let's try it. The first night and the second night. These are actually Clyde Tombaugh's discovery images of Pluto. And Pluto was very close to the position that Percival Lowell had predicted Planet X should be. And so prediction was made, discovery was made, New York Times headline on the day of the announcement of the discovery, 9th planet discovered, first found in 84 years. Neptune was the one, lies far beyond Neptune, so far so good. Sighted January 21st. Search begun by late Percival Lowell. Good. Special photo telescope. Good. Makes thorough check. Good. The sphere possibly larger than Jupiter. Meets predictions. Those are the big problems. Those are actually, that little phrase right there contains the entire story of why Pluto was a planet and is no longer a planet. Possibly larger than Jupiter, I'll show you in a minute how untrue that is. It's wrong by about a factor of 50,000. And meets predictions. This is an interesting story in science, how science can go wrong. Science will usually correct itself when it goes wrong, but one way that scientists can fool themselves is to predict something, discover something, and assume that because they had predicted this thing and they discovered this thing, those two things must be the same thing. Turns out Pluto was not the object that was predicted. Pluto has zero effect on the orbits of Uranus or Neptune. And in fact, we now know, many years later, that Uranus and Neptune do not have any measurable perturbations at all. There is no planet X modifying Uranus and Neptune's orbit. What there really were, it was actually, like the original theoretical astronomers, it was bad observational data. See, don't trust the observers is a good rule of thumb. It was both bad observational data, and we actually didn't know the mass of Uranus and Neptune very well. And that actually is critical for seeing how they perturb each other. So until the Voyager spacecraft flew by Neptune in 1989, Neptune, 1989, that was when it was finally determined for certain that there is no planet X out there perturbing the orbits. But it was too late for the solar system because it accidentally got Pluto as a planet because it is possibly larger than Jupiter on the first day in the New York Times. And so of course it's a planet if it's possibly larger than Jupiter. Even Clyde Tombaugh was a little bit dubious because he knew that if it's possibly larger than Jupiter, first off, I should be able to find it easily, and I can't figure out which one it is. Which one is it now? When it moves, I'll see it when it moves. There it is. I know it's that one. So if it were possibly larger than Jupiter, it's not that? See? Clearly, it's not a planet because I can't find it. So I don't know which one it is. But if it were larger than Jupiter, it would be a big ball. So actually, it must have been fun to be an astronomer back in 1930 because I read back in all the papers I could find about why people thought it looked so small, even though they knew it was possibly larger than Jupiter. And my favorite explanation that I saw in 1930 was that it's actually, so it has to be massive if it's going to perturb Uranus and Neptune, which it doesn't, just to be clear, but they thought it did. So it's massive, but it looks small. So what's the explanation? The explanation that I read was that it has a core made entirely of uranium. This is 1930. They don't yet know that's a really bad idea. And then surrounding that core is a liquid oxygen ocean. So liquid oxygen, so it's bigger than it really looks, and even better, the liquid oxygen, it acts like a lens and make it look smaller. It's the craziest idea that you could possibly come up with. So in 1930, you could do these crazy things, and people wouldn't laugh. They probably laughed back then. Turns out there's actually a real explanation for why Pluto looks so small in this image. Anybody know why it looks so small? It's small. Oh, that's right. That's the answer. I keep forgetting what the answer is. So in the whole debate about Pluto being a planet, not being a planet, it's often lost just how small Pluto really is because of these lunchboxes, like Eugene mentioned, where the planets are all shown at more or less the same size because it makes a better lunchbox. I'm just going to show you the real sizes of the real planets just to remind you how small things are. So this is the solar system if you actually put everything to the right scale. This big yellow thing in the background is not the sun. This is Jupiter. Jupiter is huge. Saturn, without its rings, huge. Uranus and Neptune. The four up there are the terrestrial planets, Mercury, Venus, Earth, Mars. The little dots you can barely see through there are the asteroids. The biggest one is the asteroid Ceres that you might have been watching images from as the Dawn spacecraft is in orbit around it, taking those cool pictures. The other ones are the largest asteroids. The criterion for inclusion is that you have to be as big as one PowerPoint pixel, and that's how many are. Literally, that's true. So don't blink. There is Pluto. It's really kind of small. It really does not fit the pattern of what you would think would be the next planet out there. And I would also like to point out it's actually not larger than Jupiter. No. It's really not, really at all. Okay, so, and of course the other weird thing about it is the orbit. If you look at the orbits now, just the giant planets, Jupiter, Saturn, Uranus, Neptune. If you put Pluto on there, it has this really bizarre orbit where it just kisses the orbit of Neptune right here and then goes way far out and comes back in. And what's more, if you take this and you turn it on its side and you look at them all the planets are in one disk going around the sun, and Pluto is tilted by about 20 degrees. Totally bizarre. Nobody really knew what to make of it at the time, and even at the time, in 1930, there was an argument about whether we should call it a planet or not, but In 1930, if it's the only thing you know out there, it's the only thing, it's the only thing that's been discovered recently outside of the asteroid belt, which is way inside here, might as well call it a planet. Pluto's, the beginning of the end for Pluto started in 1992 with the discovery of the second object beyond the orbit of Neptune. That was made by someone who was a postdoc here at Berkeley at the time, Jane Liu, working with Dave Jewett in Hawaii. And I was in the office next door, and she came and told me all about it. I'm like, wow, that's weird. Maybe there's only one of them. And the answer is no, there's not only one of them. There are thousands and thousands and thousands. This is even an old slide. I should put more of them on there, of objects in this region that we now call the Kuiper belt. The little blue one is Pluto. It's just one of these, and it's actually, if you look at its orbit, it kind of shows you the whole range of the main part of the Kuiper belt. But every single one of these objects in the Kuiper belt has an orbit kind of like Pluto's. It's maybe elongated, it might be tilted one way or the other. They're kind of random in all these directions. So even back before we were smart enough to demote Pluto and not call it a planet anymore, by like 2002, it was pretty clear that Pluto naturally belongs with this population and not with this population. And if you look at the sizes of the objects in the Kuiper belt, there's Pluto. There's Eris, the other big one that Eugene was telling about, which he says is about the same size, which is a true statement, but the correct statement is it is 25% more massive than Pluto. That's the important point to remember if anybody ever asks. Which one's more massive? Eris. So this whole belt of bodies out there. So it was a very natural. I like to think that all you have to do to understand why Pluto is not a planet is just look at this plot of the real sizes, and you're like, oh yeah, okay, it's not a planet. But what was interesting is that the demotion of Pluto was all fun and games, but the real interesting stuff was the finding all these other objects out there in the solar system. So I just wanted to give you that quick introduction to remind you about what was going on with Pluto, and I'm going to now move into more of these things in the Kuiper belt. This next object I'm going to talk about it's about a third the size of Pluto. So its size is actually not that interesting. Its orbit is what's interesting. And at the time it was discovered, it was pretty obvious that it was probably the most important discovery that we had made in the Kuiper belt, even if we didn't know why. We knew it was important. We couldn't quite tell why. Let me show you why it's so important, what's so interesting about it. Here are these objects I showed you again in the Kuiper belt. This discovery was in 2003, so this is all the objects that we knew in 2003. I could fill in some more. We discovered this new object, and this new object was very different because it was way out here. Yeah, wow, that's the right reaction. Let's try that again. We discovered an object, and it was way out here. Wow. Thank you. So when you find something way out there, you have your first reaction, besides wow, which is a great reaction, is might be a planet. It's pretty far away. To see it at all at that distance, it has to be pretty big. And we don't know how big it is when we see it, but we know it has to be pretty big to see it. Might be a planet. One of the first questions we had is actually very much like the Bouvard question. What kind of orbit does it have? Does it have a circular orbit like the other planets? Or does it have more of a cometary orbit? Does it come in to the Kuiper belt and go back out? Many objects that we know come in to the Kuiper belt and go back out. So it's not entirely surprising that we found some objects at that distance. The question is whether it stays at that distance or whether it comes in closer. So the answer, it turns out, remember the question is circular orbit or does it come in to the Kuiper belt? The answer is no. The answer is it's almost at its closest approach to the sun right now, and then it goes much, much further away. It's a 15,000-year orbit around the sun. And this is the object that's called Sedna. Sedna, we get to name all these, actually, so if anyone ever wants to ask about crazy names, you should ask me, because most of these names I got to come up with. Sedna is the Inuit goddess of the sea. She lives in an ice cave under the Arctic Ocean, and so we were looking for an appropriately cold name, and it seemed like a pretty good one. She also had her fingers cut up by her father, which is kind of creepy. But anyway, so Sedna was clearly a really weird object. What's weird about Sedna is not that it takes 15,000 years to go around the sun, that's okay. What's mainly weird about Sedna is that it never comes close to a planet. The distance from Neptune to Sedna is further than Neptune to the sun. So to be on this crazy elongated orbit like this, we don't think anything forms on elongated orbits. To be on an elongated orbit, something has to kick you into that orbit or pull you into that orbit. So at the time we discovered Sedna, we had a couple, we didn't know. We had a couple of interesting speculations. We said maybe it was a passing star that's now not around anymore. Maybe it was a lot of stars early on in the history of the solar system. Maybe it was a planet. That seems kind of stupid. But we had all these crazy ideas, but we didn't know. So I'm gonna now quick fast forward through some history, and I'm gonna do it in the way that we did it too. I'm gonna show you now this other depiction. There's Sedna again, and I want you to think about two things when I'm gonna show you these other objects. One is, think about Sedna, the direction that Sedna points from the sun is like the hand on a clock. And so that has some angle. Sedna is currently pointing down this direction, and that is, in our coordinate system, which must be a weird coordinate system, that's 90 degrees. So it must be 0 as this direction, sorry to say. So Sedna is at 90 degrees, and the other thing that I'm plotting on here is the closest it ever gets to the sun. Closest it ever gets to the sun is nearly 80 of these things that we call astronomical units. Astronomical units is the distance from the Earth to the sun. So it's basically 80 times the Earth to the sun distance. You don't care about any of that. What you should care about is the distance of Neptune. Neptune is this bottom line right here in blue. That's how far Neptune is. And this is about as far away as normal objects in the Kuiper belt get up here. This is weird. So to find something way, way, way up there really looks like it's been pulled away from the sun in some way. Very strange. Turns out, actually, just a year earlier, another object had been found that wasn't quite as extreme, but still had some of the same properties. It was pulled away from the sun a little bit, and interestingly, about in the same direction as you can see up there. And at the time that the astronomers who discovered it said, I don't know, maybe a planet, maybe it's just Neptune doing weird things, who knows. Nobody really had any good ideas how it could have gotten there. A couple years later, actually one astronomer from Brazil looked at these two objects and said, a big planet way out there could pull both of those out and cause these things. And I think he was roundly ignored, mostly because everybody knows there's no more planets out there, and that's a ridiculous suggestion. So everybody went on, and a couple years later, there was another object, and it was a little bit pushed out. The other reason that he was ignored, I think, is because these are pushed out a little bit, but maybe not that significantly. And this one, if there's only one of them, there are many, many explanations. You don't need a planet for it. So there was another couple. Look, there's another one. This was an important one when it was found a couple years ago. The other one that's pushed out the most. And again, very interesting that they're all off here in this same direction. At this point, when these five that were distant and pushed off in one direction had been discovered, is when I first sat up and took notice. I had discovered the one back there and had said, maybe a planet, maybe something else. But when this last one was discovered, like it, and it was clear that all five of these distant things were all pointing in one way, I was like, something funny is going on here. And I don't know what's going on, but there's something funny. And so whenever there's something funny going on that I don't understand, I stand up from my desk and I walk 4 doors down to my colleague, Konstantin Batygin, who's also a professor in planetary science down at Caltech. He is a pure theorist who understands all these things in gory detail, but you really would not want to get him in a telescope. It's a bad idea. And I'm sort of the opposite. I can go through the physics, but I really don't think in the same way that he does. So he and I are really an interesting combination. If you ever are outside of our office, you'll hear the two of us arguing in different languages, and it'll be really unclear what's going on to any of us. But he said that's really interesting. He said, are there other objects that are doing that too? And I was like, what? It turns out that there are 2 more objects that aren't pulled away, but they're actually the 2 other most distant objects that are in the solar system. So if you take the 7 objects with the most distant orbits in the solar system are all pointing off in one direction. So the first thing we thought was, it's not a planet because that's dumb. So we tried really hard for about 6 months to come up with all sorts of other crazy ideas for why it's not a planet, because planets, everybody knows there's not a planet out there. That's a crazy idea. And we could not figure out how to make it work. So we looked at these objects again. Let me show you. Okay, so what's also interesting about these objects, they're not just all pointing off in one direction. I just showed you the top-down view. If you look carefully, they're all actually tilted compared to the solar system. You can see the solar system in there. And they're all tilted in about the same direction compared to the solar system. So it was pretty suspicious that something was holding all these things together. You should not find 7 objects all pointing in one direction, all tilted in one direction. And we were trying to figure out what was going on. And so with much reluctance, I have to say, we decided, he sat down and actually could write it down on the board and show that a planet could do it. It could be a planet. And what we thought is, it must be a planet that goes, I asked my daughter early on about this. She's 11, she was 10 at the time. Like, if you saw these, where would you put the planet if it's going to keep them in place? And the answer's obvious. You put a planet that comes all the way around all of these things and sort of herds them in place and keeps them from moving around. And that's the obvious answer where the planet was. And we decided to try to simulate this on a computer. So what we did is we started the beginning of the solar system. We put a big, massive planet on an elliptical orbit. We put a bunch of objects on these other elliptical orbits, and we waited to see what happened. And we knew what's going to happen. Here's I'm going to show you this movie. You know what's going to happen. So here's the planet. You can't. It's a little washed out now, but the planet is in this pink. Every one of these blue things is an object that we put into the Kuiper belt just to see what would happen to it. And we know what's going to happen, right? All of these things are going to disappear, and it's going to be left with just these that are here. So let's watch. This is going to be 4 billion years. Hope you brought dinner. Here we go. They're starting to go. When it turns green, the green ones are so close in that we don't care. We only care about the distant ones. You can't really see the green. But here they go. They're starting to, here we go. Here we go. All right. They try to come in here, but they keep moving. Every time they come over here, they move around and go back. Here we go. Notice that there are many, many times fewer objects than they were to begin with. Things have been cleared out, but they're not clearing out the right way. In fact, they're doing exactly the opposite of what any reasonable person would expect, is that they are generally being cleared out of this region, and they are being trapped into this region, this very broad region, exactly the opposite direction of the planet. Now, to me and to Konstantin, this was bizarre, because we're talking a massive planet here. The planet that we tried out was about the size of Neptune. And if these objects, every object here crosses the orbit of that planet at some point, and crossing the orbit of the planet, eventually you're going to get close to it, and it's going to give you a kick out of the solar system. And that's bad. So we did not, after 4 billion years, no. We were totally opposite wrong. But look at that. Totally makes something that looks not dissimilar to what we see in the solar system today. We didn't believe it. We thought we'd done something wrong. We went and double checked, and it took us another 6 months to really figure out what was going on. And it's actually an interesting, it's an interesting thing that happens. It actually turns out to be more or less the same thing that happens with Neptune and Pluto. Remember how I told you that Pluto kisses the orbit of Neptune, just goes just inside of it? The only reason that Neptune doesn't eject Pluto is because they're locked into this very special orbit where Pluto goes around 2 times precisely for every 3 times that Neptune goes around. And so whenever Pluto is inside the orbit of Neptune, Neptune is on the other side. These guys all do exactly the same thing with this massive planet, and that's the only reason that they stick around for all this time. It really was not what we expected, but it fits what we saw in an incredible way. Let me show you again what this planet, where we think this planet is. Not only is it the opposite direction, but again, as we sort of guessed, it's in this. These things are in this tilted by a little bit. The planet needs to be tilted by about the same amount to do the things that we think it did. So this was our first year of this project, and we were at that stage, which I like to think of as the French Academy stage, We were very pleased with ourselves. We were willing to clap for ourselves. Yeah, a very nice, cute mathematical demonstration. Neither one of us really believed there was a planet out there. One, it's ridiculous, right? Everybody knows there are only 8 planets. But this was, there's only 7 objects. It just didn't seem like a good enough explanation. And besides, people have been saying there's a planet for 170 years, and they have always been shown to be wrong, or have had bad data, or have had bad theory. And generally, if you say there's a planet out there, your colleagues will laugh at you. So we didn't really want that to happen. And everything, we couldn't explain everything. There were actually some interesting things going on from our simulations that didn't make sense to us. And one of them is, we found that if we were going to make these objects stick around the way that they're sticking around, we made another set of objects too that it's very different. I don't have a good picture of what the prediction is, so I'm going to try to picture this for you. Okay, imagine the sun is here, the planet goes like this, all of our objects go like this. The other thing that happens is that through a complicated set of gravity, the objects that go like this occasionally turn, the orbits turn sideways and they move this way, or their orbits turn sideways and they move this way. So they turn, if you look at it from the top down, it almost looks like wings coming off of this pattern that you see here. This is inevitable. You cannot get rid of those wings, and we don't have wings. Our solar system, sadly, I guaranteed to Constantine, our solar system doesn't have wings. And if you predict that there have to be wings and there are no wings, you know you're wrong. This is one of the nice things about these theories. It makes these very big predictions. And we were sitting there scratching our heads, pounding our faces on the table, trying to figure out why there were these wings when they weren't wings. Maybe it's this, maybe it's that. And at one moment, I just had this inkling in the back of my mind that, actually, maybe they're not wings, but I knew there is at least one object whose orbit is perpendicular to the planets of the solar system. So I looked up its parameters, and it wasn't a wing, it was more like a wart or something. But it led me to look at a whole collection of objects I hadn't thought about, which are things that go in closer than Neptune, which, if you remember that plot of the Kuiper belt, there were a lot of them. I actually ignored those because I thought Neptune would ruin everything. But it turns out, if you look at the objects close into Neptune, there are some objects that come in perpendicular and then go out really long distances. There are 5, in fact. And we tracked these 5 objects down and had their parameters. Constantine was sitting in my office. I'm like, okay, I am going to plot these on the screen, and we're going to see where they are. If they're wings, it's because there's a planet. If they're not wings, we're wrong. And we put them on the screen, and I'm going to give you the illustrated version of what they look like here. They are the green ones, which are, you can't really, it's not quite working out, but they look like lines almost, because from above they're perpendicular, and they're the wings. They are exactly where they were predicted to be. This is a moment, so as a scientist, you don't just want to do cute math that explains something that you already knew. You want to make a prediction about something you didn't know. Usually this takes a while to verify your predictions. This, because we were dumb enough not to have looked at this to begin with, this was a prediction and verification in about a couple of week period. When we finally found these wings, we were, I would say, this is the moment that was our eureka moment. This is the moment that our jaws hit the floor, and it went from, in our heads, cute math that we should all clap at, to, okay, let's call up Berlin and see if they'll go try to find our planet for us. This is when we knew there was something really out there. So we are now firmly convinced, and so it's been even a year since that moment now, and many, many other things we've now realized a planet in the outer part of the solar system explains many other unknown things about the solar system that I'm not going to get into the gory details today. Gory details, if you want the gory details, I'm talking at 4 o'clock tomorrow in a much more technical seminar, but it's the gory details. But let me tell you some of the fun things about this planet. First off, we of course call it Planet 9 because a couple of reasons. One, it's the 9th planet. 2, it really irritates people who love Pluto. And it just cracks me up. So that's the main reason we call it Planet 9. This is how big it is. To have the effects that it has to be at least 10 times the mass of the Earth. Actually, these days we think 15 to 20 times fits a little bit better. So that puts it at Neptune, Uranus, Neptune mass. If it's 10, it's a little bit smaller. But Uranus or Neptune, this is a substantial planet in the outer solar system. This is 5,000 times more massive than Pluto. This is not one of these things that we're going to argue about whether it's a planet or not. When we find this thing, it's the 9th planet of the solar system, and it will be a pretty amazing thing to do. So the question, of course, is where is it and how are we going to find it? Well, one of the interesting things I showed you is that I showed you how it's tilted. Its orbit is tilted with respect to the solar system, and we can figure out what that tilt is. We know what that tilt is because it's tilted the same way that those very distant objects are. If it's tilted with respect to the solar system, that tells us something really good, which is it tells us where to look for it. We don't need to look over the whole sky because we know the swath of sky that it's in. So think of it this way. Here's the solar system. There's planet 9 and its orbit. What I want you to look at is not just the orbit, but the constellations behind it. This basically tells us the path through the sky that planet 9 takes. We have to go, and then it disappears. Nobody knows why. And it comes back. We have to go find it. There's actually Taurus right there. Aldebaran, Orion would be right down in here. We need to go search this swath of sky, and we'll find it. It's actually a little bit better than that because we also know, the other thing that we know is that it's on this very eccentric orbit, and we know which part of its orbit it is where it's close, and which part it's where it's far. We know how big it is. So we know how bright it is when it's close and how bright it is when it's far. When it's close, it's actually pretty bright, for astronomers. In the sense that it is an object that people with really the top-end backyard telescopes could see it when it's close, which will be about 7,000 years. Hold on to your telescope. So we know it's not close because it would have been discovered easily by then. And we can go systematically through all the times when astronomers have looked around the sky to rule out various places in the sky where it is and isn't. And in the end, we can figure out that it most likely has to be at its most distant from the sun, which is also not surprising. That's where they spend their most time. Interestingly, when it's at its most distant from the sun, it can only be spotted by the biggest telescopes we have on Earth. Here are some of the biggest ones and some of my favorite ones. The two in the middle here are a favorite around here. These are the Keck telescopes that are run by a partnership that includes the University of California and also Caltech, where I am. So many of us astronomers are on these two telescopes a lot. They're great telescopes, but they're terrible for one thing, which is looking for faint things in the sky where you don't quite know where to look. They're terrible because they don't specialize in that. They specialize in studying things in gory detail when you know where they are, but not in finding things where you don't know where they are. So all the big telescopes on the planet specialize in different things. One of the telescopes there, though next door, it turns out, is the Subaru telescope. The Subaru is the Japanese national telescope. It's not named after the car. The Subaru is the Pleiades in Japanese, which is why the Subaru logo, the Subaru car logo, is the little Pleiades. I drive a Subaru, which is why I get to, no, it's not. I do drive a Subaru. So the Subaru telescope has specialized in a couple of different things, but one of the things they've done particularly well is taking images of vast swaths of the sky at once. And I'll show you how in a minute, but that's what we want. We don't know exactly where it is, so we need to cover a lot of sky to find it. Once we find it, we will then use things like the Keck telescopes, but we'll also use Hubble Space Telescope, the James Webb Telescope once it's up there, ALMA, everything else you can think of we'll be using once we find it. Let me show you how they specialized in taking pictures of vast areas of the sky. They built themselves the largest astronomical camera in the world. They used to have a camera that was pretty big called Supreme Cam, or Supreme Cam. It's a bad pun in many different ways. Supreme Cam, but then they built a bigger one, so it's called Hyper Supreme Cam. And it is the camera. This is not the telescope. This is the camera. The camera is bigger than an anime character. It includes the largest lens ever built. This is a lens that's on the camera. The lens was actually literally built by Canon. It's the largest lens they ever built. It's the largest It was. Now it's not quite anymore, but it's almost the largest electronic detector on a telescope anywhere in the world. And it covers this huge swath of sky. The amount of sky that it covers, it's impressive to me. It won't be impressive to anyone other than me. It covers about this much sky in one shot, which is, yeah, it's pretty huge because it's bigger than the moon. Here's the full moon is there. You can get the whole full moon in one shot. And those Keck telescopes that are great, that I love, that I use a lot, the biggest that they can cover in one shot is right there. That's about 80 times smaller. So the Subaru is, without a doubt, the premier instrument in the world to cover this. We've calculated that we need about 20 nights on the Subaru telescope to cover all the area of the sky that we need to find Planet 9. 20 nights actually sounds like a pretty small number. It's an interesting number that's somewhere between trivial and impossible, which is actually a good place to be. If it were 2 nights, trivial. If it were 200 nights, kind of impossible. 20 is bigger than an astronomer typically gets on a big telescope like this, but it's not crazy. Over a 2 or 3 year time period with a large collaboration from Japan, we think that we'll be able to cover this region in 20 nights. So I think within the 2 to 3 year period at the Subaru telescope, I think we will find Planet 9. We're not the only ones looking, by the way. So we've been very good about publishing very detailed maps for anyone who wants to look for where we think it is. So there are many other groups around looking. I would like to find it myself because it'd be more fun for me, but if somebody else finds it, that's great for them. We've actually been out there to Subaru once. I want to show you now the one picture that you might never see again. This is me, right there. This is Konstantin Batygin, theorist, at a telescope. Danger. He actually hit his head. Goes good. He was wearing a hard hat. That's the camera, way up at the top there. That is even in this view, it looks huge. It's bigger than a person way up there at the top. That's why this telescope can see these vast areas of the sky. So I just want to give you a tiny picture of how much of the sky we're going to look at this fall. And we make these calculations of where we think it's going to be. You can't quite see it in green, and how big the field of the telescope is, and that's our swath that we're going to do in the fall. And this means nothing to anybody except for the occasional astronomer in the room. But let me show you what I want you to leave thinking about. So I want you to leave thinking about a couple things. One is that there is a new planet out there. We were pretty convinced 6 months ago when we first published our paper. In the ensuing 6 months, we've learned so much more. I am willing to say that if there is not a massive planet out there, that the solar system has got some really weird stuff going on. There are so many little details that this explains perfectly that I am as certain as you can be about anything in astronomy. I am certain it's out there. And I want you to think about this as actually real. This is not a French Academy clap your hands abstraction. This is a real thing in the sky. Here's what I want you to do. I want you to wake up early tomorrow morning and before sunrise. Everybody promise. And I want you to go out and look east. In the pre-dawn sky, you're going to see Orion. You're going to see, there's Orion. You're going to see, there's the Pleiades. Think about Subaru when you see the Pleiades. There's Aldebaran and Taurus. And when you look at these, when you look at Taurus right next to Orion, I want you to think this is Planet 9. Planet 9 is probably right there in Taurus. The area that we think that we need to search to find it is right there. It's probably right there. If you could pick an area of the sky to put it that you could describe to people where it was, if I said it was in Sagittarius like Pluto, some of you would know, but other of you would be like, I don't know where that is. If I say it's like right next to Orion, everybody can go find Orion. Go find Orion. Okay, you don't have to get up early if you don't want to. Wait for a few months, it'll be up a little bit later. But when you see Orion, I want you to think, it's Planet 9. Planet 9 is out there to be found somewhere in this swath of sky. And we might not find it this year. We still have a couple more years that I think we need to do to find it. We may not find it this year. Someone else may find it this year. But I really do think that within the next 2 or 3 years, that you will be, picking up the newspaper opening up Twitter, or there'll be an embed in your head, and it'll blink up and down. The Planet 9 is spotted. I think we know it's out there. I would almost say we have discovered its existence, and now we just need to spot it to know precisely where it is. I'm going to leave you with an interesting thought that this is all quite prescient of. This, of course, is our modified version of the Plan 9 from Outer Space poster. I don't have to tell that to an audience in Berkeley. But Ed Wood, when he probably approved this poster, was quite prescient in a way that I didn't even realize until I looked really carefully at this. So Plan 9 from Outer Space. God, I can't remember the plot. There's, alien. Yeah, okay, maybe there's no plot, but it involves Vampirina and Boris Karloff and all this. But the aliens are making. I actually can't remember, but there's an important scene that takes place here in the graveyard. And if you blow the poster up really carefully, nobody knew this back in 1969 or so, but it actually says, R.I.P. Pluto right there. Who knew? Who knew? Thank you very much.
How many days separation between two photos would you need to be to see it?
Yeah, so it's a great question. It's so far away. The question is, if we take a picture, I showed you those pictures of Pluto. Those were a day apart, but you don't even need to see Pluto. You can do it an hour apart. We need 1 night of separation between our images to see it, and which is actually great. It's not. It's moving fast enough that if we take a picture of the sky, and we come back to the same spot the next day, it moves by just this perfect amount, just a little bit more than the size of a star itself. And it doesn't move by a huge amount, so it's easy to find these things. It'll be when we point to the right spot in the sky, we'll take 3 pictures in a row over 3 nights, and it'll go tick, 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 and that'll be it. I'll drop my laptop instead of dropping the mic or something, but we'll know where it is. It's going to be very exciting when it happens.
Yeah, right next to the question.
So presumably a planet of this size had to come from somewhere, like maybe the accretionary disk.
Yeah. So where did it come from? This is actually one of the more exciting things because it's not just the goal is not just to go spot it and say, "Ha, we found a planet." Actually, that's the goal. But the goal is to find a planet, study it, learn about it, figure out what it's telling us about the solar system. So where did it come from? We don't know. So let me start by saying we don't know. We can tell you that there's a mass out there doing something. We can't tell you anything about its history yet, but we can speculate. Might be in the fiction section of the books. But let me tell you our favorite speculation on where it came from, because it actually makes sense. Maybe 10 years before all this happened, Konstantin Batygin, who was my partner in crime on all this, and I were working on an entirely different problem that we were interested in, which is, what would happen if there were a 5th giant planet early on in the history of the solar system? How would it affect the planets that we know and the Kuiper belt? And so we did computer simulations, put in 5 giant planets, and what always happens when you put in 5 giant planets, almost always, one of them gets ejected. And we didn't care. It gets ejected. Who cares what happens when it gets ejected? We only paid attention to what signature it left as it was being ejected. It now seems pretty obvious that once you're ejected, one thing that might happen is that you don't get ejected all the way, and you eventually find yourself in a Planet 9-like orbit. I think the most likely explanation is that it is something that formed in the region of Uranus, in the region of Neptune. That's why it's about the same size, mass as those guys, and it got ejected. So interestingly, in many different ways, Planet 9 makes us seem more like other planetary systems that we see around the galaxy. We see other stars that have planets that kind of look like they might have a similar history to them. So it's not a bizarre idea that we might have had something like that ourselves.
Is there a relationship or a formula that would indicate the maximum possible distance from any given star that you could have a planet go around?
Yeah, so the question is there some way to figure out what's the most distant you could have a planet out there? And the answer is yes. It's not a simple formula that you could do, but it's really, so there are a couple things. First off, gravity goes forever. So the only thing that makes the sun the sun influence not go forever is that there are more stars in the galaxy. So parts of our solar system, this thing called the Oort cloud, the other sorts of comets, Eugene talked about the Kuiper belt having comets, the Oort cloud also has them. It's halfway to the nearest star. So that is tremendously further away than anything we're talking about here. There might actually be large objects out there in the Oort cloud, but they're on kind of not very stable orbits. If you really wanted to be on an orbit that's been kind of stable for the age of the solar system, you wouldn't want to go more than a couple of times further than we think Planet 9 is. At that point, you start to get influenced by stuff on the outside. So right now, we think Planet 9 might be its furthest extent. It might be 10,000 times the Earth-Sun distance. If you went out to, I say 10,000, 1,000 times. If you went out to 5,000, things get iffy out there.
It's just the distance to the next star.
That's what the distance to the next star, and also the overall effect of all the stars in the galaxy are what really make the difference.
Right here in the corner.
Yeah, you had that wonderful simulation with those proto-Sednas or whatever.
Yeah, proto-Sednas, I like that.
You posited, you can use it,
Thank
you. And you posited a planet. Is that a mass scaleless diagram? How much math did you assign?
Oh, so no, it was not scaleless at all. So I didn't go into the details, but we had to pick. We actually did thousands of simulations to figure out what mass we needed. If you have too little mass, nothing happens. If you have too much mass, everything gets ejected. And so
That one that worked, and it stirred the pot without reckoning.
yeah, and we actually before we found one that worked, we actually had calculated from just analytically what we thought would work, and it turns out to be about right. And that's where we come up with something like 10 times the mass of the Earth.
In the far back.
Yeah, have you been able to observe anything about its composition without directly observing?
So no. So the only thing we know, do we know its composition? No, we don't know. We know its mass. That's it. All we know is it's a point mass. It might be made out of hamburgers. It could be made. People ask me, what if it's a black hole? The answer is, it's not a black hole. But if it were a black hole, I don't care. If it's 10 times the mass of the Earth, it can be a black hole. But it's not a black hole. What if it's two objects orbiting each other? It's not two objects orbiting each other. But if it were, I don't care, as long as it's 10 Earth masses. However, I can tell you something about things that are 10 times the mass of the Earth. Because that's about the most common mass of a planet that we find in our galaxy. If you'd asked me this question 10 years ago, I couldn't tell you anything about it. But now we know many, many stars have planets that are about 10 times the mass of the Earth. And by and large, we think that that most of them that are 10 times the mass of the Earth are gas giant planets rather than like rocky Earth-like things. So it's rather than scaling Earth up, you scale Neptune down. So we think that's most likely its composition. Also, that's what you would get if you formed in that Jupiter, Saturn, Uranus, Neptune region. So this is the speculative part, but I think it's a pretty good speculation of what it's going to be like. However, when we spot it, we will then get to use things like, the first thing we'll do is use the Keck telescopes to look at light reflected off of it to learn about its composition. When the James Webb Space Telescope gets into space, it will be a fabulous telescope for studying it. So we have many other things to learn when we actually finally spot it.
So probably not uranium.
It's probably not a core of uranium, and it's probably not surrounded by a liquid oxygen ocean. That is fair to say.
Right in the middle. Do you expect Planet 9 to have Trojans like the other planets?
So the question is, do we expect Planet 9 to have Trojans? So let me first explain what that means. That if you look at the orbit of Jupiter, on those scales that I showed you here, I wouldn't have shown you anything. But if you look at Jupiter in particular in our solar system, goes around the sun, but just in front of it in the same orbit by 60 degrees, and just behind it in the same orbit by 60 degrees, there are thousands and thousands of objects, little asteroids, circulating with Jupiter. There are these very special, stable spots where you can put things that are stable for the age of the solar system. And Jupiter has them. As far as we know, Saturn and Uranus don't. Neptune does. The Earth occasionally kind of gets things there. They don't really stay. Would Planet 9 have Trojans? And the answer is no. Planet 9 would not have Trojans because that crazy elliptical orbit doesn't allow those same stable spots to be stable. So Let me make sure I believe that when I said it. I've never actually thought of it exactly that way. You occasionally get things that share its orbital period. It's possible. Yeah, you get things, but so they're not Trojans, but you get things in the one-to-one resonance. Yeah. They're actually not, so they're not co-orbital. They have the same semi-major axis, which is in the case of a massively, but they're one-to-one. But they're not in the same orbit. So I'm not going to call them Trojans. But yeah, you can get.
Mike, would the trajectories of Uranus and Neptune be affected? I mean, we know them pretty well.
Yeah, the answer is yes, but at the scales of tens of kilometers, and we don't know them that well. So actually, the thing that we know best, it's an interesting exercise to ask yourself, what's the best measured large-scale distance that we know of in the solar system over a moderate time period? Anybody want to guess? I can't hear. So I'll tell you the answer. The best measured distance over a decadal time period is the distance from the Earth to the Cassini spacecraft around Saturn. So that is a precisely measured distance. Cassini's been in orbit around Saturn for more than 10 years now, and it's been precisely ranged, and so people know exactly where it is, and have built these models of everything in the solar system based on this, and people have tried to use perturbations to that to see if you can see Planet 9 pulling Saturn a little bit, and it turns out that there are enough other things that are close that have more of an effect on that distance. So it's not the position of Saturn, it's the distance from the Earth to Saturn. And you can move around the Earth by just a little bit by making the passing asteroids a little bit more massive or a little bit less massive. And that's more of an effect than Planet 9 has, because Planet 9 is so far away. So far, nobody has come up with a way to use any current knowledge to find a perturbation. God, but I wish I could, because that would not just tell us that it's there, but that would point in the exact direction. That would be fantastic. Early work suggested it might be possible. I think we've now proved it's not true. Anybody who has good ideas, go figure them out, tell me. I'll go look.
Have you and the team been through the data on the Kuiper objects enough to set a lower limit as to what another Planet 10 might be?
So it's a great question, which is basically, I'm going to say, if there's a Planet 9, why not a Planet 10? Why not a Planet 11? And I actually love this question because this is, if there's a Uranus, why not a Neptune? If there's a Neptune, why not a something else? We get to ask these questions now. The last decade has been so boring. Like there are 8 planets. If there's 9, there might be 10. How are we going to find them? So right now, the answer is we cannot tell you anything about Planet 10. If there is, if there isn't, if there's evidence. And the reason is because the evidence for Planet 9 is these objects who have orbits that are sort of similar to Planet 9's distance away. Planet 10 has to be even further. We don't even know of any objects out there. They're going to be fainter. They're going to be hard to find. Planet 10 is going to be fainter than Planet 9. Planet 9 requires the biggest telescopes we have in the world. So I give this talk often for groups of kids and explain, Planet 9 is the perfect planet for our generation. It's things that we can find now. It's telescopes we have now. But if there's a Planet 10, it's not me. It's not people I know. It's kids. It's the next generation of astronomers are going to go off and have to find this Planet 10, which is so much better than saying, oh no, 8 planets, suck it up.
Are there any probes that are currently flying to the outer solar system now that if in a couple of years from now you knew where to go, you could actually change their orbit? So it's the interesting question about whether any probes are on their way that are maybe going the right direction, that you could maybe redirect. And so there's 2 answers. One is that no, turns out none of them are going the right direction. And 2 is none of them have fuel. You cannot redirect any of these spacecraft even more than so unless you had gotten really lucky. But it's cool to think about, how do you get a spacecraft out there? Could you get a spacecraft out there? I've actually been, for like the last 3 or 4 years, I've been working with teams at JPL on when I say working with teams at JPL, it makes it sound like I actually know something. They're working and I'm like clapping my hands on
how to get things to the outer solar system really quickly. This was not anything to do with Planet 9. This was before we thought about Planet 9. This was because many people are interested in different things in the outer solar system. And the answer is actually there's current technology that could get you out there pretty quickly. You know, whenever we send a spacecraft to the outer solar system, we do a gravitational slingshot around Jupiter to get things sped up. Turns out there's even a better gravitational slingshot in the solar system, and it's the sun. So you go straight in, slingshot like mad off the sun, and you're going really fast. So the actual technical hurdle turns out to be shielding. How close can you get to the sun without burning yourself up? So we're working on that, but at that point, it still will take you 50 or 60 years to get there. But I actually think that when we find it, it will provide the incentive to really start to think about these fast missions pretty quickly. So I'm actually kind of excited about this, in the sense that you can be excited about things that happen after you die.
There's a question right behind the bar.
So if you find this Planet 9, what are you going to call it?
If I find it, what am I going to call it? That is a jinx, and I'm not going to answer that question. No. And I have not even thought about that. I mean, people ask that question all the time. I literally refuse to think about it and have not thought about it, really, honestly. Although, I will say that my daughter has a name that she has picked out. She has two names. Her first suggestion was, call it Pluto, so Pluto can be a planet again. And her second suggestion, her name is Lila. Her suggestion was, call it the Lila planet. I'm like, oh, that's good. Okay.
Did you give a lecture using natural history 5 years ago?
Yes.
At that lecture, did you describe that there was a planet and you could tell how it was determining the orbits of these objects that you found, and you saw the effect of these on these planets? And if you know the mass, why can't you exactly tell where it is? Because it's determined.
Okay, so let me get the two questions. Did I talk about this 10 years ago? The answer is yes, because 10 years ago is right when we had discovered Sedna. And so that talk in New York, I remember this talk because we had just discovered Sedna. I talked all about Sedna and how maybe a planet is doing it. I didn't actually think it was a planet. We actually thought it was it was just one at the time. Trust me on this one. I remember this. But we talked about that. But the other question, what was the other question? Mass. Oh, why can't we tell you right where it is? So the question is, how come we're so bad when Leverrier was so good? I think is really the question you're asking. Leverrier said, it's right there. Go look. And it was right there. One night, they found it. We say, it might be here. We might need 20 nights, and our telescopes are bigger. The reason is Leverrier had it a little bit easier. He had a full orbit of Uranus to watch the perturbation. So if Neptune's here, as Uranus goes around, it's a little slow here because Neptune's tugging, slow, normal, fast because Neptune's tugging. Basically, it's a big sign that says, I'm a planet and I'm over here. None of the objects that we have made any appreciable movement in the 10 years since we've known them. Sedna, we know for 10 years. Sedna has a 10,000 year period, so it's moved that much. If you could wait for 10,000 years and you told me its position for 10,000 years, I would point at Planet 9. So we don't have that one extra piece of information. It is amazing to me how much we've been able to tease out from what we do have. I still am holding out hope that there's some clever way that we can figure out exactly where it is, and we have a few tricks we're working on. So far they've all been total failures, but we have hope.
One last question here. Yeah, maybe the last one.
Okay, this is kind of irreverent, but given the way the planet Pluto was named, or why it was named Pluto,
Are you going to ask me about a name? Because I'm not going to answer. If you ask me about a name, I'm going to stick my fingers in my ears.
it's my understanding
No.
PL from Pluto is for
Percival Lowell.
well, maybe the M-I Mickey?
So just to be, although this is speculating about a name, I will say that when it is found, even if I'm the one who actually spots it with the telescope. This is me and Constantine, who I talked about the whole time. If it were just me, we would not know anything about this planet. If it were just Constantine, we wouldn't know anything. It was this really. It took the two of us, who are very different people, finally learning to speak each other's language through a lot of screaming and yelling and arguing in a good-natured way, to really finally make sense of both what we're seeing in the sky and how to interpret it. It's been like a tremendously enjoyable 2.5 years for me working on this, because I've learned so much and I've enjoyed working with him so much. So he's got to be in there too. That's all I'm going to say. And then I'm going to stick my fingers in my ears. Can we have a question that's not about a name? Because I'm not going to answer questions about names.
Very last one. So, do you have any idea of when Planet 9 would have been ejected? Was it caused by like Kuiper migrating inwards, or just...
Yeah, when was Planet 9 ejected? I said it got too close. It was ejected. It most likely happened very early. So the solar system, that simulation I showed you, was 4 billion years. The solar system in the first even just 100 million years, even shorter than that, was really going through all kinds of perturbations and rearranging itself. And in those very earliest perturbations, it would have done it. It needed to have been early for other reasons, which is that just ejecting it isn't good enough. You have to eject it and then have it not escape completely. It's actually a little bit like the problem of Sedna early on, of being ejected but then sticking around. That makes it's easier to do if there's still some other stars around, which would have been early. So we actually think it was really early, 10 million years maybe maximum, when all that rearrangement took place.
Okay, great. Well, let's thank Mike again for